in Southeast Missouri State University and in the University of Texas, and then he joined the Texas Christian University in 2011. John is a sedimentologist with specialty in fluvial systems, both in modern and ancient environment. He has won multiple teaching awards, and in particular, most notable is the 2015 Distinguished Lecturer Award of the AIPG, which we will hear 2 talks from that series. So this morning he'll be talking about a tale of earthquakes past and yet to come, a cautionary account of New Madrid faulting from the Mississippi River. At 3 o'clock today, he'll be talking next door in 101 about time in the rock, a fluvial view towards preservation of time and process in the stratigraphic record. And finally, next week, in this room, Wednesday, we'll hear David Weinstein from Eilat, who will be talking about coral reefs, asking, can modern reefs accrete? Thank you.
Thank you very much. Well, thank you very much for inviting me here. I've always, I grew up kind of in eastern Kentucky and very much in the Christian church, and this is obviously one of the places that everybody where I came from always wanted to eventually get to. So I'm very pleased to have the opportunity to be here. And today I'd like to share, though, a little bit of the work that I've done with fluvial systems, particularly with the Mississippi River and the New Madrid Fault Zone. So if you live in the States, the Mississippi River is our main drain, so it's the main river that drains the continental U.S., and the New Madrid Seismic Zone is the main earthquake hazard in the mid-continent. So everybody there's heard of it, but I think the other thing that I want to talk about more than anything else today is a little bit about what we learned fundamentally about how fault systems work from using the modern sedimentary record and how we've been able to dovetail those two to add some insights into a little bit about what we know about seismic hazard these days. So, a tale of earthquakes past and present, a cautionary account of the New Madrid Fault in the Mississippi River. Well, first off, let's kind of catch everybody up to speed. First off, is my accent? I don't have one, do I? All right. Yeah, good. I always thought everybody else did. Anyway, but nonetheless, if you listen to country music, you know this accent. And Yehuda told me I have to say the joke. My county has produced more million-selling country music stars than PhDs. All right. Anyway, so let's catch everybody up a little bit on the background of the geology of the New Madrid Seismic Zone. First off, this is the New Madrid Seismic Zone. It sits along the Mississippi River at right dead center of the continent. So right in there is actually the hazard zone. So this is the 2% probability hazard map of the United States. So as you can see, there's a large area of concern along the west coast, which everybody's heard of the subduction zone in the northwest and the San Andreas Fault down here in California. But this big bullseye right here in the middle is the New Madrid Seismic Zone. So it's our second biggest hazard area in the United States. As far as why it is there, well, it's somewhat comforting to know we haven't answered all the questions. We have ideas. There's 2 things most of the ideas have to do with the idea of some sort of warm rift pillow under the U.S. weakening the crust. But the 2 things that we do feel comfortable about the New Madrid Seismic Zone is, one, the crust is pretty weak here, and this tends to be a zone of weakness where we see lots of strain taking place. And also, the total amount of actual displacement in the area is very small, on the scale of a few millimeters a year. So the cumulative amount of strain that's being put on this system isn't very large, but yet it's generating very large earthquakes. How large? Well, historically, we start with the New Madrid earthquakes. They're a large cluster of earthquakes that happened in the early 1800s, and they have some historical importance. First off, they're what's often called a triplet. So, first earthquake happens at 2 a.m. on 12/16/1811. right here in this area, down here around what they call Marked Tree, where absolutely nobody lived. Okay? Then, that morning at dawn, you got another earthquake that's largely considered a very large aftershock, but it was still in the scale of being a great earthquake. It was over a 7. So this one happened to be, though, right under one of the local towns. So it's actually one of the 2 most destructive earthquakes that happened in the series. Then you went through a long period of about a month or so, and then actually it was January 23rd when the next big one hit, and that was here, around this little town here. Of course, it didn't do a lot of damage because guess what? The town right here had already been destroyed by this one. All right? So then we went a little bit longer. On February 2nd, we had what's called the New Madrid earthquake. This destroyed the town of New Madrid up in this area, and it's the namesake for this series. But essentially, there's 4 large earthquakes happening out of this. Okay, as far as what it did, historically, we know a few different things that happened as a result of this earthquake. First off, we know there's surface deformation, which I'm going to talk about at a lot more length. We also had fairly significant landslides all along the bluffs of the Mississippi River, the scars of which are still there. You get a lot of these. These are called sand blows locally, but they're essentially sand eruptions. So they're essentially sand dikes from ruptures that burst out on the surface violently and threw sand maybe as much as 30 feet in the air and spread it into big circles. And so these dot the landscape around the area. So they're major liquefaction features. Okay, a couple important things about this earthquake system that are rather important for us, and also important for anybody who's looking at intraplate earthquakes, is this is the intensity distribution. So this is the 4 intensity line and the 11 intensity line for the New Madrid earthquakes. Key thing is the broad distribution of damage that these things are able to cause. This is the 1906 San Francisco earthquake, which was of comparable size and its damage radius. So the big one in California would do a lot of damage in California, but in Nevada they'd be like, what? Whereas if you had, when I remember there was an earthquake when I was growing up here in Maysville, Kentucky. It was a 5. There was only 1 reported actual injury. It was a cop who spilled coffee on himself here in Detroit. All right? So the overall length for which these earthquake waves attenuate is tremendous in these mid-continent earthquakes. It's like smacking a piece of roofing tin with a hammer. Everything shakes. Okay, the other thing that's interesting about this set of earthquakes is the longevity. So what has happened in this case, let me back up one, is this has some really important historical importance for the U.S., is that the first riverboat going down the Mississippi after we bought the Louisiana Purchase was parked right there on the morning of 1811, December 16th. So that meant that they felt the earthquake. After they got the riverboats back, they all got back to New York and Pennsylvania, New York and Pittsburgh and all these places they were from, and it littered the newspapers. So what that means is one of the earliest earthquakes where we have lots and lots of detailed press accounts of the events. So the other thing that meant then is that the minute people heard about this great earthquake, and again, remember, the attenuation distance, the old joke was it rang church bells in Boston. The reason we know that is because there were people keeping records. The minute everybody heard about this earthquake, we had the equivalent of we had the Victorian equivalent of science nerds that were basically recording every earthquake event and exactly what happened. Dishes rattled, church bells rang. The reason we know church bells rang in Boston is because 5 or 6 people accounted the specific time when it happened. So what that meant was we have a very detailed record of the long-term attenuation span of these quakes. So different months of the year, different levels of aftershock. These are the 3 big ones. So the point is the ground shook all year, okay, with moderate-sized earthquakes. Okay, one of the other things, of course, that it did is the earthquake was responsible for a certain amount of surface damage. So the fault system itself is actually a thrust fault. So it's a deep-seated thrust fault, is the real foot fault, pops up in here, and what this large red area is this the primary area of uplift. It's a hanging wall anticline. That's what it essentially amounts to. And these different places at the marks of the changes in topography are essentially the kink bands. So This is an actual uplift that's caused from along the thrust front from the 1811 earthquake and other earthquakes that happened in this area. The other thing is these are strike slip faults that attenuate off of it. So this is largely a strike slip system. This is just a wrench fault, essentially is what it amounts to. The thrust is actually an offset between two major strike slip trends. So it's a transpressional system. Okay, so the other thing that we know about the earthquakes, just largely from people who have been looking at the geomorphology of earthquakes, fault systems, and rivers for a long time, is there are several different responses rivers can have to different levels of tectonic uplift. So they can change their pattern from meandering to braided, they can be meandering and go straight for a while, they can be a little more braided to a little less braided, but there's several documented geomorphic responses to rivers as they cross over faults, simply because you're lowering the slope on the upstream side and raising the slope on the downstream side without really changing any other variables in the natural fluvial system. So the system generally has a couple different responses it can do to the sudden changes in slope. And so we've known for a long time that the Mississippi River through the New Madrid seismic zone has had these responses, particularly this one, where it's generally straighter up dip and more curvy down dip of the actual fault zone. So that was a known quantity. Okay, so where my research picks up is here. Somewhere along the line, got the idea, let's go in and say, we know that we've got an active fault system here. We know we've got a major river crossing it. We know that rivers respond to tectonic effects. Why don't we look into the sedimentary record of that river in the recent past and see if you can actually see those effects being preserved in the stratigraphic system and use that as a paleoseismic tool to see if we can reconstruct something about the earthquake systems of the past. So we're using a refined mapping of Mississippi River Holocene sediments and a refined chronology of Mississippi River events to do this. Okay, so we start with allostratigraphy. Essentially, we're just mapping based on disconformities. And so we pick out the main mapping units, oxbow lakes or abandoned channels, point bars, and start mapping the fundamental fluvial features in the system. So we do that using remote sense data. That looks like a channel to me. And so you say, well, if that looks like a channel, you start drawing it in, and you have preliminary maps where they've done the same sort of work. Then, after that, you've developed a hypothesis map that simply says, what do I think is here? Then you send some students out to drill some holes. Okay? And then that's the beauty of it. We can do that as advisors, right? So the thing is that they drill holes, and what they're doing is they're going to the landforms and simply asking the question, is the stratigraphic sequences one would predict from those landforms present at those locations? So it's just simple hypothesis prediction test. I think it's a channel fill. If it's a channel fill, it should have one of these different lithologic signatures. And if it's a point bar, it should have one of these. And so you simply hypothesis prediction test. If it comes out that your prediction stands up, then you map it in. And before you know it, you've got some kind of a sense of what the distribution of the landforms are in terms of a stratigraphic record. Then we get some relative and absolute and numerical age relationships. So we use things like soils, better and less developed soils to get an idea of which are the older landforms, but also we do a lot of, and cross-cutting relationships, but also we do a lot of numerical dating. So we use a combination of carbon-14 and OSL dating to date the individual meander loops and the individual river patterns. So there's two things that we did on this particular study that turned out to be firsts. First off, this was the first time we successfully dated individual meanders in the Mississippi River system based on radiocarbon, because it's really tricky. There's so much reworked organic matter that literally what you have to do radiocarbon dating here is you have to go to very specific stratigraphic points where you know exactly what should be there, and then we drill and we drill and we drill until we come up with just the right thing that a biologist can recognize and say, yes, that's a seed, yes, that is a rework, and yes, and then we date that. So most of the whole soil samples produce completely spurious results. And there's enormous amounts of reworked coal from the Appalachian Basin here, so there's a lot of dead carbon in the soil too. So functionally, A little care in the preparation of the samples got us to the point where we could confidently date radiocarbon individual meander loops. Then the next thing we did is we went with OSL samples. So with OSL samples, we're sampling the actual sand. So we drill a hole down into the point bar, and we pull up a core with a suction tube. Then we seal it off and send it to the lab. And so there what we're doing is we're sampling very discrete intervals in the point bar. And we're sending them off for OSL, and we get an OSL data back. So the other side is this was actually the first time OSL data was used to date individual meanders too. Oddly enough, we weren't the first ones to publish it. Nightly beat us out by a year because it took forever for us to get anybody to disbelieve we actually did it. But anyway, we did. So this is where we ended up. So this is our map of the Mississippi meander belt across the New Madrid sighting zone with all the discrete point bars and all the discrete channel fills, all characterized according to age. So the red is my early Holocene, the green is my middle Holocene, and the yellows are my late Holocene parts of this particular channel belt. Okay, so now let's step back to what we already knew about the New Madrid seismic zone independently before I got involved with it. First off, earthquakes. We already knew that there were a series of earthquakes. Matter of fact, there were not just the 1811, 1812, but there were actually two earlier clusters of earthquakes that had happened on the New Madrid seismic zone that were well documented. So first off, we knew about the 1811, 1812, remember, nerds in basin. We also, from paleoseismicity, particularly liquefaction features around the area and dating of those, and also trenching across the actual hanging wall monocline of the Reelfoot Scarp, there's been dating and definition that defined at least two more episodes of offset on the Reelfoot Fault. One at 1450 AD and one at 900 AD. So they're roughly, so each one of these was a cluster of its own. Roughly they were triplets. Each one of these was a triplet. And they're roughly 500 years apart. Problem though is prior to 900 AD, the signal pretty much went dead. So there's no evidence of uplift from the scarp or sand blows that tell confidently that there was anything happening from the years 1000 BC back up to about 900 AD. So we have about 1900 years there where there was not just no evidence of displacement on the Reelfoot Fault, there was evidence that there was no displacement on the Reelfoot Fault. So the idea was essentially this thing just came alive in the AD 900. Okay? Which also did explain one thing, is why there's only 8 to 9 meters of actual deformation on this system, is because clearly because it wasn't running very long. However, if you looked at the whole post-Holocene, there's about 15 meters of offset on this thing. So clearly there must have been something happening in the Holocene before 900 AD, but no actual record of it existed. So this is where we came in. So first off, what we started to do is to start to reconstruct the actual channel patterns of the Mississippi River. So this is what we got from the dates of the individual meander loops. We could thread a channel through the 900 AD Mississippi River. And so this is what the 900 AD Mississippi River would have looked like. Right after 900 AD, though, it started a series of cutoffs. I think he will. There we go. After 900 AD, it started a series of cutoffs. So it started right there, attempted that cutoff, then it did that one, then it did that one. So right after 900 AD, within about 200 years, that's what the Mississippi River looked like. So the Mississippi River straightened its course, but only on the upstream side of the Reelfoot Fault. So essentially, that makes sense. 900 AD was the first major deformation event, no deformation before that. The fault kicks. And immediately after, the Mississippi River starts to straighten its course because of the lowered slope, gets rid of all those little switchbacks, makes a straight course. That was the expected response, and sure enough, when we looked in the stratigraphic record, what we found is it wasn't the 1811, 1812 earthquake that caused the modern straightening of the river. It was actually the first event, the 900 AD event, and it's been pretty much straight ever since. So that was something that was completely predicted by the paleoseismicity. The river simply reproduced exactly what they said should have happened, The river's meandering, doesn't care what's going on in the real foot fault for about 1,000 years, and then 900 AD, your first earthquake, you get about a meter of displacement, bang. The river decides to respond and straighten. For the next two earthquakes, well, the river's already straightened, so it can't pull that trick again. So what it does instead is it starts dumping splays off to the side and grading the upstream side of the fault, where the slope is lower, and incising on the downstream side. So incised here about 3 to 4 meters on the downstream side, and graded about 2 meters here on the upstream side to try to level the course back out. And there's two discrete splay events separated by a paleosol, a mollisol to be specific, one for the 1450 AD event, one for the 1811, 1812 event. So the river had another response for the two later earthquakes. It straightened on the 900, splayed and incised for the 1450 and the 1811, 1812 earthquakes. Okay, so the story could end there, but it didn't. And so far, all I've done is I've told all the people who have been doing paleoseismology that the river agrees with you. It says everything that you said should have happened is happened pretty much the way you said it happened. But here's where the problem set in, is when I stepped back here and looked at the mid-Holocene part of the system, well, that is the course of the Mississippi River 4,000 years ago, about 2000 BC. That's what it did right after 2000 BC. It pulled the same trick. It went from a highly meandering, highly sinuous river and then straightened out in this little course at about 2000 BC. Okay, so that's a long time back. The other thing is if you look at this pattern right in here, this cross-section along the straight ridge, it's actually incised about 1.5 meters. So it not only straightened, it actually cut down. It's a discrete new course the Mississippi did when it changed its pattern just on the upstream side of the fault. Then what it did was it decided after that, after about 1,000 years, about 1000 BC, to avulse actually to the higher floodplain, which rivers don't do that. They don't like to avulse from a low course to a high course. But of course, it has to cross that. So if you pop that uplifter up in front of it and create a steeper slope there, it has to go around it. So anyway, so there's a period of about 1,000 years where the river is maintaining a straight course until it abandons it. In 2000 BC to 1000 BC, exactly like it did from 900 AD to the modern. And in between, it's meandering. And before that, it's meandering. It pays no attention to the fault. It's as if it isn't there. All right, so what do we think that means? Well, first off, this is the deformation on over the real foot fault on the hanging wall incline, prepared by Van Arsdale, simply by doing good old structural contour mapping and simply mapping the different surfaces up through the base of the Eocene, up to the base of the Holocene, and all the way through back to the Cretaceous. And of course, there's been some activity on that fault for, well, back into the Cretaceous. But if you look again, what you see is from Cretaceous to recent, the total deformation is really small. As the Paleocene to recent, it's a little faster. Neogene to recent, it went back slower. For the whole Holocene, the total deformation rate is about 1.8 millimeters a year. That's about how much uplift we get on this fault. But if you look actually at AD 900 to recent, it's 6.2. So essentially, we've got mismatched rates. So it clearly isn't doing this rate for the entire Holocene. It would have accumulated 3 times the deformation that it actually did. Whereas if you look at this number, if you look at the total amount of Holocene deformation, and then you divide it by the 900, you divide the AD 900 by 3, they work out pretty well. That makes some sense. So here's what we think happened. First off, we really don't know much about what's going on in the early Holocene because that's all the record we have in that little red patch. But when we get into the 700 to, when we get up into 6,000 AD to 4,000 AD, the river's meandering. It's essentially showing no effect of the real foot fault. It's going across it like it isn't there. There's no evidence of any uplift on the fault. And then about 4,000 years ago, that's when it straightens. And it maintains that straight course for about 1,000 years before it goes back to its meandering course once again for about 2,000 more years. And then after that, it goes into the modern slip cluster where it straightens out again. And from about 900 AD to the day, 900 years, it's been straight again.
So essentially what we think is going on here is the Mississippi River is the Reelfoot Fault is recording temporal clustering on millennial scales. It's going has periods of about 2,000 years of quiescence, and then you'll get about 1,000 years of high deformation, and then it'll go quiescent for about 2,000 more years, and then go into a new slip cluster, in which we are now in the present slip cluster, which represents about a third. It was representative of about a third of the time of this particular fault system over the course of the Holocene. Okay, so what really ends up being the thing that's different here is, of course, if you're just looking at the paleoseismology, you get that slip cluster, then that quiescent, and that record ends here. The Mississippi River actually is the one that says, hey, guess what? This is a repetitive occurrence. The modern thing you've seen is actually something that's been going on for the Holocene, repeating itself in these millennial scale slip clusters. So, millennial scale temporal clustering means faults shut on and off. Thus, seismicity does not always equal threat. Okay, that becomes the real kicker in here, is that we're looking at the New Madrid seismic zone today while it's active, and we see all these earthquakes. But if you were looking at it the other 2/3 of the time, it would basically look pretty quiescent. But yet you would see all this evidence of past deformation. You'd see all these liquefaction features and all this uplift and so forth, but you wouldn't actually see any active seismicity. So that brings the next question. Do we have other faults around this area like that? Well, actually we do. Okay? So there's the Wabash Valley Fault, and that's a sand blow from the Wabash Valley Fault. It's generated some fairly significant earthquakes in the Holocene, but it's fairly seismically quiescent right now. We get a few little earthquakes off of it once in a while, but not a lot. There's the Commerce Liniment. From the Pleistocene on, we've got on the order of about 80 meters of displacement in places on this fault. But again, right now, every once in a while, you'll get a 4. It'll rumble a little bit, but you get very little actual seismicity. And then what's happening now, which is the bigger concern, we're starting to see some seismicity on the southern Reelfoot margin. Essentially, all of these faults in the Reelfoot are generating from an old alocogen that was related to the Proterozoic rifting of Laurentia away from the supercontinent. And so this is the failed rift arm. And most of these faults, the earthquakes are happening on these deep-seated faults. So this has been the main Cottonwood, main strike slip center. This is the actual rift margin. It's coming awake right now, which has got Memphis really worried because it sits right there. Okay. So anyway, the point of it is there's other things like the New Madrid seismic zone that would look like the New Madrid seismic zone if it was in its phase of quiescence. Okay? So it's always the quiet ones. Okay. So what that means then is faults. So one thing that has been broached by this, of course, is faults potentially in this area trade off their actual strain. So thus the most seismically active fault is not always necessarily the biggest threat. It just depends on where you are in the time sequence between their trade-offs, right? Okay, so let's look at something else here. There's our faults again. There's our December 16 fault. There's our other December 16 fault. There's our 123, January 23, and boom, there's the New Madrid fault on February 2nd. There's not a lot known about that particular earthquake, right, in this area here. This large aftershock is the one that actually destroyed the town of Little Prairie, and it's the one that's closest to a lot of the actual infrastructure. And so we set about trying to understand it a little bit better. And so we went down there and once again did the same trick, did some allostratigraphic mapping in this particular area. And there's our Cottonwood Grove Fault. That's the major strike slip trend. And there's the actual geology of the meander belt sitting above it. And here's what we found, is right there over the Cottonwood Grove Fault, when you drill enough holes in the area, what you find is the actual top of the point bar is warped down about 2 meters in this particular area across this fault. So you get a major downsag. But the other trick is that it's filled in with this big, huge splay, so nobody noticed it. So it's flat down there. There's no actual indication there's anything going on there. Until you start drilling the subsurface and find the actual floodplain muds over this point bar are actually bent down pretty, I'd say about 2 meters. There is historical evidence here, though. This was the site of one of one of Fuller's 1811 sun plans. He went out he was with the U.S. Geological Survey, and he went out on the 100th anniversary of the New Madrid earthquakes and just started trying to recover a lot of these historical accounts and a lot of these locations and to find several of these places he called sun plans, where there was record and there was still evidence this land had actually subsided during the earthquake itself, probably. And so essentially this sun plan is in one of our sites. The other thing is, if you look real close, there's concentrations of lateral tears and sand blows right around this area. They're pretty intense. Matter of fact, if you look at the map of liquefaction features around this Penobscot County, it's a Native American word, literally means sea of mud. But whoops, sorry, went too fast on that one. There we go. If you look here, this particular cluster of liquefaction features sits right here at this site. Here's the other trick, is when you look at the soil map, it reproduces this splay that we found. The soil map shows this large splay feature sitting right here and filling this topography on the down-thrown side of the fault, which came out with this isopack when we started drilling holes there and trying to find the mud veneer underneath. We actually mapped out this splay. So essentially, what has happened during the 1811-1812 dawn earthquake on December 16th, we got a major, well, this is right lateral. I know my structure. Yeah, right lateral. Okay, fault, strike slip fault, and so we have a sag in this area, probably a little bit of transtension, and this area warps down. Of course, what happens is immediately this big massive splay breaks out of the river, plops in here, fills that thing up. It fills that thing up. I think I figured it was like about 35,000 cubic meters of sediment, just plops into this hole and fills it up fairly quickly. So it sort of buries all of our evidence right off the bat. And so when you actually look around again, it's pretty much flat there. There's no evidence of a scarp till you start to dig. And so on this side of the scarp, you get this big splay. There's our mud veneer down in here, and there's our splay pile. And if you dig up in here, there's the mud veneer right on the surface. So the mud veneer is actually warped down about 2 meters. Okay, so, and again, this is the actual distribution of thickness of that splay. So there's sort of the epicenter area right there around this 2 meter sag. Okay, and there's the splay coming in, filling the low topography. One thing that we do get out of this one that you don't usually get out of an 1800s fault is a historical account. So again, remember, like I said, that the riverboat, first riverboat going down the Mississippi was parked here. It was literally docked just a few miles up from this earthquake when it happened. And so the riverboat comes down immediately, comes to the town of Little Prairie and goes, what the heck? It's level. There's one guy there. And this is what he said. He said, here's the falling of trees. The swamp at the back of the prairie was completely inundated. The bank was much broken by extensive longitudinal fissures, and we saw water gushing out of several transverse zones, which must have extended back at least as far as the swamp. Sounds a lot like a splay to me. Okay? So we actually have a historical account of the levee actually breaching and plopping that splay in there and filling that thing up during the 1811-1812 earthquake. And of course, that existed as a sump land. And people have recorded this as what they call Big Lake, a large area that was actually a tectonic depression that developed during the 1811-1812 earthquake up into Fuller's day. Now the next question becomes did that whole splay happen in the 1811 or 1812 earthquake? Because we know there was a splay plopped in here, but the question is all this deformation related to the 1811-1812 earthquake, or just part of it? So that's when you get in here and start doing some dating. Of course, the real problem you have here is it's very difficult to just date Mississippi River mud. I tried to actually do radiocarbon on it once. I just got a reduced pile. I just had this brilliant idea where I work in the Cretaceous. I'll send it off to my palynology friends, and they'll reduce this down to a carbon film, and I'll date that. And then he sent it back and says, I could have told you that this was a Mississippi sample. It was full of Mississippian pollen. Okay. Again, you rework the coal fields. And so those spores out of those coals have unbelievable longevity. And so there's huge amounts of reworked carbon in this stuff. So that was worthless. And so you can't date OSL on the muds. And really, you couldn't pull off on the splays. And I was frustrated. I was walking around this trench in here trying to find some of the bunch. And I kept tripping over that log. And as I kept walking over, tripping over, then I started digging the log out and realized this is a cypress tree that actually fell over the mud veneer and was buried by this way. I have never collected a radiocarbon sample with a hacksaw and a hammer before, but these things are tough. This cypress log has been buried down there, dated it, and guess what? 1810, plus or minus 7 years. So anyway, the point of it is this, remember the history of the falling trees, the earthquake knocked down most of the trees. Well, this is one of those trees apparently got knocked down over the mud veneer, and it actually got buried, then it got buried by the splay. So we got a radiocarbon date of it, and it's right there at the bottom of the splay. The whole thing happened in 1811, 1812. So there's no actual evidence from this particular splay of the 1450 or the 900 AD fault. Okay, so what happens next? Well, that means we don't know what happened in those other faults. What we do know, though, is this is the proposed epicenter for the 1811, 1812. Well, here's the punchline. Okay? This is the Cottonwood Grove Fault that actually recorded the major earthquakes of the 1811, 1812. This is what's called the axial fault system. Have a note, the Cottonwood Grove Fault system, there's no seismicity on it. All the seismicity is on the axial fault system right beside it. So again, these two are evil twins. They're trading off the seismicity. The axial fault zone is actually the one that's seismically active. It's the one you regard as the threat. The one that actually did the damage is doing nothing today. There's one. Remember I said there was a 1450 and a 900 AD earthquake as well. Well, the 900 AD earthquake and the 1450 are not recorded by that splay. But what we did do is we drilled a lot of holes through that splay, and we finally got to get a reasonable map of what's under it. Okay? And so here's what we found, is if you looked here, there's a meander complex of the Mississippi River that was totally expected, but there's this smaller simple channel belt with all these little breakouts right in here. They record a split flow and a breakout of the Mississippi River into this area. And so this is what we call a breakout. Essentially, it's a little distributive system that built off of the main Mississippi River channel, and again, it probably carried pretty much most of the Mississippi flow at one time. But this breakout channel splits out in here into this large depression, and that's what's under the splay. So when we started trying to get some sense of how that worked, that would be what the breakout would have looked like. Well, that's also one of the things we expect when you have rivers crossing a sag. If you drop a pretty decent sag in that river, then the river will often go to a little distributor pattern for a little bit while it fills the hole. And you get a little bit more of an anastomosing or a distributive pattern that's filling a tectonic low spot, if it's a sufficient low spot. And what's a sufficient low spot? Remember, 1 meter of uplift on this fault erases 1 meter of uplift on this fault erases about 30 kilometers worth of gradient. Actually, erases 10 kilometers worth of gradient. But what we found is it only takes about 14% slope change, based on work Shum did up and down the Mississippi River. It only takes about 14% slope change to actually get a response out of the Mississippi River. So if you can erase 10 kilometers with a meter of uplift, you can completely disturb 30 kilometers worth of river path with that uplift. This is 2. So it's plenty enough to do the damage. Okay? So even though we look at a big river like the Mississippi and go, well, it's a big river, it can handle anything. The reality is it's got its feet of clay. Its problem is that it actually has a very, very low gradient. It's only about 10 centimeters a kilometer. So if you put a meter of uplift in front of it, that's a huge slope disruption. Okay, so what do we got then? So this is all downstream. So this is down in here from the main belt. So what we did is we started dating this. And so figuring out when this breakout happened. Well, we got some dates from the loops that precede, that are cross-cut by this system. And we got dates of about AD 400, AD 10. Then we dated things in and after this breakout. They came out about 80. The feeder loop itself came out about 8970. Subsequent loops about 8970 to 1070. Key thing is that this breakout happened between about AD 710 and AD 1050. That's right where the 900 AD earthquake happened. So this particular breakout and sag seems to be tied to the 900 AD earthquake. So now we actually do have some evidence of the 900 AD earthquake at this same spot, as well as the 1811 and 1812. And so that works. But we do have one bit of a problem. We've got the splay recording the 1811, 1812 earthquake. We've got the channel breakout recording the 8900 here. But where's the 1450? So there's no evidence at all about the 1450. Not only that, there's evidence we don't really have a stratigraphic place to even put the thing. Nothing seems to have happened, which is a bit curious. But let me introduce you to this guy here called the Boot Hill Liniment. Okay? The Boot Hill Liniment right in here, the Boot Hill Liniment is this guy right in here. So the Boot Hill Liniment is essentially a break that goes from the Cottonwood Grove strike-slip fault and connects strike-slip straight to the northeast unnamed strike-slip system and bypasses the transpressional real-foot fault, thrust fault. Thing of it is it's, as you can see from the seismicity record, it's functionally inactive seismically right now. There's nothing really going on in the Boot Hill Liniment, but there's a bunch of sand blows, a bunch of liquefaction features, and well, turned out a friend of mine, Peggy Uccioni, went in there and started looking at this thing, and what she found is that actually slipped in 1450. So there's really no evidence prior to 1450 of it slipping, and it didn't slip in 1811, 1812. But she noticed offset streams and so forth and fill related to slip on that fault strictly in the 1450 event. Okay, so the Boot Hill Liniment seems to be where that missing 1450 event happened. Okay, so what that means is it sets up this scenario. So there's our earthquake happening on the Cottonwood Grove Fault at 1811, 900 AD, causing the river breakout. 1450 AD, the seismicity shifts, the Boot Hill Liniment is the one that slips. Then back in 1811, 1812, it's back to the old spot on the Cottonwood Grove Fault. So they're switching back and forth. Although the Boot Hill Liniment is seismically quiet right now, it actually was probably the one that was responsible for the 1450 event. So again, it's the quiet ones. Okay, so what's all that mean in terms, so that's kind of what's going on in the Mississippi River, and I think the big takeaway from all that is that what we're finding from looking at it is the earthquakes, one is the earthquakes aren't necessarily correlated today with the faults that actually did the real damage in the past. And two, what we're finding is the major seismic problems in the New Madrid seismic zone seem to be clustered over very long periods of time. And they'll shut on and off as sets, both temporal clusterly over the millennial scale and temporally clustered over the yearly scale. So, I'm not the first one to say earthquakes are fractal, but functionally, we've got a hierarchy kind of set up here where they're clustered on 1,000-year cycles and they're clustered on these yearly 500-year cycles where you'll get clusters when they do occur. So we know that about the fault system. In the bigger picture, though, what's happened over the years is this, when I first did this research, this was, well, let's just put it this way, it wasn't immediately accepted. But essentially it was because the way that we usually do seismic hazard and the way we have traditionally done it is we simply ask the question, where are the earthquakes happening? Where have they happened in the past? That's where they'll happen in the future. So we use the Gutenberg relationship and we simply say, this fault has had a history of slip every 100 years. It'll slip again in 100 years, high probability, and we make probability estimates based on that recurrence interval. However, if the faults that are actually doing the damage aren't necessarily the seismically active ones, and major fault systems shut off and on, well, that doesn't work quite as well. You have another element of hazard. So here's where that kind of kicks in. Okay? This is the Sendai earthquake where the Fukushima disaster happened. There's the tidal wave coming in. We're all pretty familiar with the devastation that this thing caused. It was one of the big earthquakes in the recent past, 2011. That is the seismic hazard map right before the earthquake. Red is bad. Okay? So the key point is that this was one of the lowest seismic hazard risk areas in Japan. Why? Because they hadn't been getting a lot of earthquakes there. It was just saving up. Right? course, this is actually some work Seth Stein did. He and his students from Northwestern, he kind of shared this with me. He's been following up on this idea quite a bit. But anyway, this is some work in China. Of course, they've been keeping records of earthquakes for a very long time in China. And so these are evidence of earthquakes from 1300s to 1550. This is 1550 to 1660. This is 1660s to 1678. This is up to today. The key point is that when you look at them, there's not really this consistent pattern of these earthquakes seem to happen on the same fault. They're shifting around considerably. So what that means is when you start thinking about what's the probability location of the earthquake, if you have to factor this in, then heads, 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 heads doesn't mean the next one's heads. It means it's still an equal probability of heads and tails. And so if you start having to think this way, you have to factor it in. Well, you might change the way you would redo a seismic hazard map. So this is something Seth put together for the Transylvanian area. And essentially, this was the seismic hazard map he put forward. I'm sorry, based on historic seismicity. This is what it would look like if you just based it on essentially what faults are there and what probabilities might exist for their activity. So, what this all means. Well, interplace seismicity reflects non-steady state behavior of a fault system, and again, this is one of those things that I think as time's gone on, and especially, there's been some good work done here on the Dead Sea, and there's one West Side Total Fault. There's a lot of things where this is not an idea that is necessarily brand new, but it's something that has not necessarily been the mainstream thinking. It's becoming a little bit more of a thing. Earthquakes in mid-continents are episodically clustered and migrating. Continental aftershock sequence lasts a lot longer in mid-continent areas than plate boundaries. Also, the biggest one though is that if you are simply looking at seismicity from the point of view of the faults that are seismically active are the ones that are the most threat, well, that's not a bad place to start. But it also offers the potential of overestimating the hazard in recently active areas and underestimating the hazard in other places. So with that, what does it all mean? Well, again, it's one of those things, if this dog has bitten me 3 times in the past, I'm going to feel pretty confident there's a good likelihood that it would try to bite me in the future. But it doesn't mean that the other dog down the street that's barking at me wouldn't bite me too. So what this means is it's as we've seen an evolution over the recent years where there's been a lot more thinking in terms of the potential of these non-active faults as potential seismic threats than just simply the ones that are active. And so what's it meant for the mid-continent? Well, this is the new Madrid hazard tree that they drew up in 2008. They've modified it a bit since, but it started about 2008. I got my own limb. All right, so thank you very much.
Seismic in the area?
Oh, well, actually 3D, no, because they haven't found a lot of oil there. So it's pretty expensive, but they run a lot of 2D. Matter of fact, they've actually ran 2D down the river and so forth, the subaqueous seismic and so forth. So there's a lot of that, and it does actually confirm most of their ideas about what the sub-thrusts are doing and so forth.
Did you look at the relation between climatic changes and the change in the pattern of the river?
Yes, actually, that's the first concern when you're looking at these sorts of things. Yeah, essentially, where my thoughts were on that is that you're really looking at a finite stretch where there's no major tributaries, and you're kind of so I am depending on the zero mass change assumption that you're not changing over that one stretch right over the fault, the mass or the mass, you're just changing the energy in the system. So yeah, that is an assumption that I'm making. It's that climate, but like I say, the basis of that is simply because I don't have anything that can really change it across that stretch. There's no new tributaries coming in, and you're too narrow to actually change the climate across that zone. It's only about 100 kilometers length. So that said, we worked in Missouri. It's climate change all over. Matter of fact, it's tremendous. The fault that we've seen up there and looking in the Missouri River, its major tributary, through the Pleistocene. I was telling Yehuda about this. We got this major lake glacial maxima terrace. Then the river cut down about 10 meters during the big flush when the Chrysler broke down. Then it went up about 7 meters at 1300, made a meandering system, dropped back down to the prior level of 10,000, then popped back up to the modern level about 10 meters up at about 8,000. It's been there ever since, but it bounces like crazy. And the patterns change from braided to meandering, and in stretches in the Holocene in 4,000 years, it's gone from horseshoe meandering to island braided to braided. It's nuts. But so yeah, the Missouri is just climate city. This one little stretch of Mississippi, there's no real change in the channels, types, or patterns, and we're dealing with this sort of short read, so we took the liberty of that assumption.
Is there any echo, a reflection of what you are showing us in the Mississippi Delta? Because you know, most of the description here was a very limited zone, which was very complicated one. It looked like the stomach of a human being. But I guess that there should be some reflection in the delta of the Mississippi. And then you have cores, and maybe these cores are giving you information for a longer period of time. Because clustering for 10,000 years, it's a very short interval.
Yeah. Well, it's an interesting point you bring up because, I guess it was Rick Alice. He was, at the time, he was head of landform dynamics at NSF because, he posed this question to a few of us because there was a theory along those lines. But, it was like I sit there and with me and Chris Paola and a couple people, we were running numbers on this, and it's like the amount of the idea was there was this big slug of sediment off of these slopes and so forth that would show up in the Mississippi and be working its way down. But the point was I started running the numbers of the amount of material that's actually displaced from these big bank slumps and so forth that had actually changed the sediment supply. And, half of it would fit in that one splay that shot in there and filled that one space. So, and neither of them really seemed to be a substantial proportion of the total load. So I guess the trick is that theoretically there is a change related to the sediment supply that could potentially show up in Mississippi, but it's how small. And the more we started to learn, which I'll talk about this afternoon, but the more we started to learn about how those sedimentary signals move through the system, we learned they really get shredded. So it would have to be huge to really do that, and it probably is just not big enough. That said, nobody's found it. But there's probably a reason. But again, we're geologists, we never say never, right?
Okay, let's thank our speaker again.
Thank you. You can have the help.
Well, actually, this statement really that predates the Holocaust. Since the we've seen some. I've been there for 200 years. And the overall modification of the actual pattern where we're looking is not that big. It does a lot of things in terms of point growth and bank cutting and a lot of consistent techniques there. But actually, in terms of modifying the larger scale patterns, it seems to be too short of a bend to register on the time span. So if I was working on a short time span, they'll probably have to but they're really a part of the big components.
GPT.